Amplitude modulation. Let us discuss the other versions of amplitude modulation. Actually, the original version or the basic version of amplitude modulation is double sideband and full carrier. That is the basic or fundamental version of amplitude modulated wave. In that particular version, or in that particular amplitude modulated wave, we have got full carrier wave, and along with the full carrier wave there are two side bands. One is lower sideband and the other is upper sideband. And the equation of double sideband full carrier wave or the amplitude modulated wave is given by this equation, that is VAM is equal to Vc sine omega Ct plus mVc by 2 cos omega C minus omega m into t minus mVc by 2 cos omega C plus omega m into t. In this equation, this is the complete equation of double sideband and full carrier wave. In this equation, the first term Vc sine omega Ct is the carrier part of the amplitude modulated wave, and the second term in which there is a term cos omega C minus omega mt is the lower sideband with the frequency Fc minus Fm, where Fc is the frequency of the carrier wave and Fm is the frequency of the message signal. And the third term, that is which contains cos omega C plus omega m into t, this is the upper sideband having the frequency Fc as the carrier frequency and Fm as the frequency of the modulated signal. So it is evident from this equation that in double sideband full carrier wave, along with the carrier wave, lower sideband as well as the upper sideband both are present. Now the important point is that the actual information or the message which we have to propagate from one point to another is the message signal, or the important information is contained inside the angular frequency omega m, which is the angular frequency of the message signal. Therefore, the complete information of the message signal is contained inside the lower sideband and upper sideband. Now, this is the case of double sideband and full carrier wave. Now, as we have already discussed in the earlier video, that the power of amplitude modulated wave in double sideband full carrier wave is given by the equation PAM is equal to P carrier into 1 plus m square by 2, where PAM is the power of the amplitude modulated wave in which carrier and both the sidebands are present. P carrier is the power needed by the carrier wave for its propagation, and m is the index of modulation. If m is equal to 1, that is if the modulation is 100%, then in that case PAM is equal to 3 by 2 into P carrier, or we can say that P carrier is equal to 2 by 3 PAM. Or in other words, we can say that if we want to send or propagate the amplitude modulated wave, then the power needed to carry the carrier wave, or the power needed to propagate the carrier wave, is 2/3 of the total power needed. And the carrier is only used for carrying the message signal. It is only the vehicle for carrying the message signal, but the power needed to propagate it is quite large. It is 2/3 of the total power needed, and this power is actually some sort of wastage of power, because the message signal is not contained inside the carrier portion of the amplitude modulated wave, but it is contained inside the lower sideband and the upper sideband. Therefore, we can say that this amount of power, that is 2/3 of total power needed, is just wastage of power. So in order to remove this difficulty, or in order to save the power, the version of amplitude modulated wave double sideband suppressed carrier is developed. Earlier version was double sideband and full carrier, that is DSBFC, in which full carrier was present. Now, in order to remove the difficulty of wastage of power, another version or improved version, that is double sideband and suppressed carrier is developed, which is abbreviated as DSBSC. So, in order to convert the basic amplitude modulated wave, that is double sideband for full carrier wave, into double sideband suppressed carrier wave, we have to remove the carrier portion of the AM wave, and then the wave will convert into DSBSC, or double sideband and suppressed carrier. As is evident that when we suppress the carrier component, then only two sidebands will remain in the amplitude modulated wave, the lower sideband and the upper sideband. Therefore, the equation of DSBSC is given as VDSBSC is equal to MVC by 2 cos omega C minus omega MT, the lower sideband, minus MVC by 2 cos omega C plus omega M into T. This is double sideband and suppressed carrier. And this equation has the, from this equation we can make out that the advantage of DSBSC is that since the carrier component is not present, therefore the power needed to carry the carrier component will be saved, and this method is useful if we have to save power in the propagation of amplitude modulated wave. Now the bandwidth of DSBSC is the total range of frequencies required for the propagation or transmission of the DSBSC, and it will be the difference of the upper sideband frequency and the lower sideband frequency, and that will be FC plus FM minus FC minus FM, that is 2 into FM. This is the same as the bandwidth for the DSBFC. It means that though the power needed for the propagation of DSBSC is reduced, but the bandwidth needed remains the same, because in the case of full carrier amplitude modulated wave, the bandwidth was 2 FM. So this is the bandwidth remains the same, only the power needed is reduced. Now the frequency spectrum of DSBSC is shown in this figure. As we can see that only the lower sideband and the upper sideband are present, and since the carrier is suppressed, therefore the frequency of FC has no voltage component, or the amplitude of this pure carrier frequency is 0. Only the lower sideband and the upper sidebands are present. This is the case when the message signal is the single frequency, that is FM. Suppose if the message signal frequency is only 200 hertz and FC is 2 megahertz, then FC plus SM will be 2 megahertz plus 200 hertz, and the lower sideband will be 2 megahertz minus 200 hertz. So in the case when there is a single message signal, then this is the frequency spectrum of DSB Sc. But in the case where the modulating frequencies they are for a particular range of frequencies, it is suppose the message signal lies from 20 hertz to 20 kilohertz, then the upper sideband will be a complete band of frequencies, that is FC plus FM. So the lower portion will be FC plus 20 hertz, and the upper this line will indicate FC plus 20 kilohertz. Similarly, in the lower sideband, this portion or the upper edge will have the frequency FC minus 20 minus 20 hertz, and the higher or the this portion will be FC minus 20 kilohertz. In the earlier slide, we have seen what is the frequency domain representation of double sideband suppressed carrier amplitude modulated wave. Now we will study what is the time domain representation of DSB Sc. Time domain representation means on the x-axis we are taking time, and on the y-axis we will take the instantaneous value of voltage of the signal. So in the figure, the upper part of the figure depicts the double sideband and full carrier amplitude modulated wave, and the lower portion of the figure or the second figure is the time domain representation of DSBSC or double sideband and suppressed carrier amplitude modulated wave. As it is evident from the two figures, if we compare these two figures, we can see that in the upper figure we are dealing with double sideband and full carrier. It means that in this amplitude modulated wave, carrier component is present in its full form. As we can see, when the amplitude modulated wave is starting from this portion, the maximum amplitude of the carrier, that is Vc, is present, and on this carrier wave we are superimposing the message signal or the modulating signal. So this is the amplitude modulated wave on the positive side of the y-axis, and similar is the case with the negative side of the y-axis, that is the full carrier amplitude is present or the full carrier component is present, and on that carrier wave we have superimposed the message signal or the modulating signal. So on the positive half complete wave is present, and on the negative half also the complete envelope is present, and this is the case of double sideband and full carrier wave. Now if we go to the second figure, this is DSBSC, that is double sideband and suppressed carrier wave. As we can easily see in this figure, the pure carrier component has been suppressed, or the pure carrier wave has been completely removed. So this portion, the starting portion of the wave, which contain the carrier portion is totally removed, and only the lower sideband and the upper sideband or the two sidebands are present in the wave, and this is the time domain representation of DSBSC. Now we have seen that the advantage of DSBSC is that the power needed for the propagation of this wave is greatly reduced in comparison to DSBFC. But we can see from these, comparing these two figures, that in the case of the upper portion, if we have to receive the original signal from the modulated signal, then we can simply remove the negative portion and the complete message signal can be retrieved from the positive axis of the y-axis. And if we want to take the negative side, then we can simply remove the positive portion and we can retrieve the complete envelope from the negative y-axis. But in the case of DSBSC, the maximum amplitude is Vm sin omega mt on the positive side and minus Vm sin omega mt on the negative side. The modulated wave extends between these two limits, or we can say that the modulating or the modulated wave goes to the positive side as well as to the negative side. And as we will see in the portion when we will discuss the detection of the message signal, it will be evident that when the signal is present in the positive as well as in the negative axis of the y-axis, then it becomes difficult to retrieve the original message signal or modulating signal. So this is the disadvantage of DSBSC signal, that the retrieval of the message signal or the modulating signal is somewhat difficult than the earlier case or the case of DSBFC. The main purpose of developing DSBSC is to save power. By suppressing or by removing the carrier component from the amplitude modulated wave, we can save a large amount of power needed for the propagation of amplitude modulated wave. Therefore, after the removal of carrier wave, only the lower sideband and upper sideband are present in the DSBSC. So, if we want to calculate the total power needed for the transmission of DSBSC, then we will have to sum up the power used for lower sideband and the power used for the propagation of upper sideband. As we can see from this equation number 1, the total power needed will be m square Vc square by 8r for lower sideband as well as the same quantity for the upper sideband. Therefore, the total power required for the propagation of DSBSC is m square Vc square divided by 4r, because the power needed for the carrier has been eliminated from this equation. Therefore, it is evident that a large amount of power will be saved in this form of amplitude modulation. We also know that the power needed for the propagation of carrier is Vc squared by 2r. So if we combine equation number 1 and equation number 2, then the total power need for the propagation of DSBSC is m square by 2 multiplied by power needed for the carrier wave. If we are having 100% modulation, that is m is equal to 1, then power for DSBSC is half of the power needed for the carrier wave. Therefore, a large amount of power is saved mathematically. We have seen it. Now, if we consider the power needed for the complete amplitude modulated wave, that is double sideband and full carrier, in which the carrier as well as the both the sidebands are present, then from the previous discussions we can recall that this power is equal to 3/2 times power needed for carrier. After rearrangement from the earlier equations, we can get the equation for D power DSBFC is equal to 3/2 multiplied by 2 times power needed for DSBSC. This we have achieved that by making use of the earlier equations. And if we solve it, then it comes out to be 3 times P DSBSC. Hence, we can say that after again it is this equation is rearranged, and the power needed for double sideband and suppressed carrier is equal to 1/3 times the power needed for complete amplitude modulated wave propagation. Therefore, the double sideband suppressed carrier modulated wave needs only 1/3 of total power needed for full amplitude modulated wave. Now we will study single sideband technique or SSB modulation, which is one form of amplitude modulation. Until now we have studied amplitude modulation, that is double sideband and full carrier, and after that we studied double sideband and suppressed carrier, that is DSBSC. Now we will study the improved version of amplitude modulation, single sideband technique or SSB modulation. We know that in DSBSC the carrier is suppressed, but LSB and USB both sidebands are present. Now we also know that the message signal frequency is contained in lower sideband as well as in upper sideband. The frequency of lower sideband is FC minus FM, and the frequency of upper sideband is FC plus FM. It means that in both the sidebands the frequency of message signal FM is present. Therefore, the information about the message signal is equally present in both the sidebands. Or we can say that individually both the sidebands are equally capable of giving information about the message signal. So, from this statement, we can conclude that if only a single sideband is received at the receiving end of this communication, entire communication unit, then if only one sideband is received, then it is capable of giving the entire information, because both the sidebands have the equal information. By making use of this concept, SSB was developed. In single sideband modulation, we transmit only a single sideband. Either the lower sideband or the upper sideband is suppressed or removed at the transmitting end, and only a single sideband is transmitted and the message signal is retrieved from that particular sideband. Therefore, we get a complete information about the message signal. Now the equation of SSB will be, it is quite evident and simple. If the lower sideband is transmitted, then VSSB will be MVC by 2 cos omega C minus omega MT, and if the upper sideband is transmitted, then the equation will be the same except the frequency component, which will be omega C plus omega M. Now, the bandwidth required for the transmission of SSB will be the difference of two frequencies. If upper sideband is carried, then it is FC plus FM minus FC, it is equal to FM, or it is FC minus FM, it is equal to FM. Hence, we can say that the frequency or the bandwidth of single sideband is half of the bandwidth of SSBFC and SSBSC. In both the earlier cases, the bandwidth required was 2 FM. Therefore, the bandwidth needed in the case of SSB modulation is half of the earlier versions. These two figures show the frequency spectrum or frequency domain representation of single sideband. If it is the propagation of upper sideband, then the lower sideband, that is FC minus FM, and FC that is the carrier wave, have been suppressed. So this is the frequency spectrum, and if only the lower sideband is transmitted, then the carrier wave and the upper sideband have been removed. So this is the frequency spectrum of single sideband modulation. As in the previous cases, if instead of single modulating frequency, we have to communicate a whole range of modulating frequencies or the message signals, then we will instead of a single upper sideband frequency or the lower sideband frequency, we will have a complete band of upper sideband or the complete band of lower sideband. It is quite evident from this figure. So it is clearly evident that if we are transmitting only a single sideband, either the lower sideband or the upper sideband, so the total power needed for the transmission of a single sideband amplitude modulated wave will be m square Vc square divided by 8R. If m is equal to 1, then it will be simply Vc square divided by 8R. And on the same lines as we have done in the previous slides, the total power needed for the transmission of carrier wave is Vc square divided by 2R. Therefore, the power required for single sideband transmission will be power of carrier divided by 4 by combining these two equations. And we know that from the earlier discussion, we can recall that the total power of a simple or full amplitude modulated wave is 3 by 2 times the power needed for propagation of carrier. So we can conclude that the power needed for single sideband amplitude modulated wave propagation will be power for amplitude modulated wave divided by 6. Hence, we can make a statement that the power needed for the propagation of complete or full amplitude modulated wave remains only 1/6 of its value when we are propagating or we are transmitting only a single sideband. And this is the greatest advantage of single sideband transmission of amplitude modulated wave. So in the previous parts of this lecture, we have studied DSBSC and SSB modulation, and we have completely understood that the main purpose of developing DSBSC and SSB modulation is to save power needed for the propagation or the transmission of amplitude modulated wave. But for each method, if some advantage is there, there are some drawbacks or some shortcomings also associated with those methods. In the case of SSB transmission, as we have calculated earlier, the power needed is 1/6 of the power needed for the transmission of full amplitude modulated wave. Therefore, we can say that we have saved up a large amount of power. But there is some difficulty with SSB also, and the difficulty is that we know that the carrier frequency Fc is much greater than the modulating frequency Fm, because the carrier frequency lies in hundreds of megahertz, and the largest value of modulating frequency is only 20,000 hertz. Therefore, if we compare these two quantities, then Fc is much larger than Fm. Hence, we can say that Fc plus Fm, that is the frequency of upper sideband, and Fc minus Fm, frequency of lower sideband, they lie very close to each other because the quantity Fm is very small quantity. Hence, we can say when these two frequencies of upper sideband and frequency of lower sideband, they lie very close to each other, then they are slightly indistinguishable. Suppose we have to remove the upper sideband, and it is so much indistinguishable from the lower sideband that if we want to remove Fc plus Fm, then some part of Fc minus Fm is also removed, because they are indistinguishable to a great extent. So if Fc minus Fm is also removed, or some traces of lower sideband is also removed, then it means that some information about the modulating signal will be lost. So to remove this difficulty, a vestige means a small trace of the sideband which we have to remove or which we have to suppress, is allowed to remain in the amplitude modulated wave along with the allowed sideband. Suppose we have to transmit the lower sideband Fc minus Fm, and we have to suppress the upper sideband, that is Fc plus Fm, then we will not completely remove Fc plus Fm, but we will let a small trace or a small vestige of Fc plus Fm in the amplitude modulated wave. Since we are keeping a vestige or a trace of the sideband which is unwanted in the AM wave, then it is therefore it is called vestigial sideband or VSB modulation. So this equation is DSBSC. Uh, Both the lower sideband and the upper sideband are present in DSBSC. In VSB, that is vestigial sideband modulation, we are keeping, in this example, we are keeping the lower sideband, that is omega c minus omega m is left as it is, and a trace or a fraction of the upper sideband is allowed in the amplitude modulated wave. Therefore, this is the final equation of VSB modulation. Now the generation of amplitude modulated wave. We have gone through the amplitude modulated wave discussion in quite details. Now we will study how we can produce amplitude modulated waves in different modes, that is DSBFC, DSBSC, SSB and VSB. The methods for generating AM are broadly divided into two categories. The first category is linear modulation method and the second is square law modulation method. In the linear modulation method, we make use of the current voltage characteristics of a transistor. If we go to the characteristics of a transistor, then we will find that there are certain regions which are linear, certain regions which are non-linear. So in linear modulation method, we utilize the linear portion of current voltage characteristics of a transistor. And making use of this principle, two methods are developed under this category. The first is base modulation method and the second is collector modulation method. For the students of LU or Lucknow University, in MSc 4th semester, the methods based on linear modulation they are not in the syllabus. Now the second category is a square law modulation method. In this method, we make use of the square law or the non-linear regions of the current voltage characteristics of a particular electronic device. Non-linear regions of current voltage characteristics generally have a variation according to square law. That is, the current is directly proportional to the square of voltage. If a device is having this kind of characteristic or a characteristic based on squared law, then these characteristics are utilized in order to obtain the amplitude modulated wave. And in the forthcoming video lectures, I will explain these methods in quite some details. Okay, thank you.